In this lecture, we are going to talk about the Cauchy's theorem, and we'll see some examples how we can use Cauchy's theorem to evaluate different kind of integrals. So before we jump down to the theorem itself, one thing we need to define first is called simply and multiply connected domains. So simply and multiply connected domains. Now, what is a simply connected domain? Let's say you have a domain like this, and you have a contour inside it like this. So a simply connected domain is something that is defined is that if you can draw any type of simply closed contours, then this simply closed contours within this domain encloses only points of D. What does that mean? So let's say this is the domain D, and this blue line is our simply closed contour, and inside this contour all the points are a part of D itself. That is what simply connected means. Another way to understand simply connected domains is that if you have a domain and you don't have any holes inside it, that means you can take this contour, that means this blue line, and you can shrink it up to a point, and this shrinking has to be continuous. If you have a hole inside it, you would get interrupted. So that's what simply connected means. Your domain doesn't have any holes. And a multiply connected domains means it's not simply connected. So let's now draw a multiply connected domain. Let's say this is some domain. There is a hole over here and another hole, let's say over here. One hole is good enough, but I'm taking two holes. Now if you can draw a contour like this, you might get confused because you can see that all the points inside this contour are also a part of this domain, okay? But if you draw a contour like this, all the points inside this contour are not a part of this domain. Why? Because see this hole over here? The points of that is let's say you are saying that this hole has some points. This hole is not a part of this domain, this black line thing, okay? Think of them as two holes or like a handle, and if you try to shrink this contour indicated by this bluish color line, if you try to shrink it, then you would get interrupted by this hole. That means you won't be able to shrink it to a point continuously. There would be a discontinuity once you reach the boundary of the hole. So these are called multiply connected domains. So this means it has some holes inside it, but while in the simply connected case, you don't have any holes. Okay? And with that, we now move on to the theorem that we have been talking about, that is the Cauchy's theorem. So theorem. This is the Cauchy's theorem, a very important theorem in complex analysis, and it tells you that if your function, let's say you have a function, if a function f, that means a function of complex variable f of, you can write it f of z, I'm just writing it to be f. If a function f is analytic in a simply connected domain, then along a simply closed contour let's call that contour C. Inside D or in D, if you evaluate this integral, then this would be 0. Obviously this is a closed contour, so use this symbol. This is the famous Cauchy's theorem, and the proof is pretty simple. Also, I want to leave some remarks over here, and the remark is that while we stated this theorem, we have to require the fact that we require that f prime of z, that means the derivative, be continuous in that domain D, is continuous in D. However, this assumption is not necessary in the Cauchy-Goursat theorem. That means there is a generalization of this theorem which basically tells you the same thing, that means the thing over here, but it doesn't rely on this assumption that the derivative of the function inside that domain have to be continuous. In fact, from the Cauchy-Goursat theorem, you can see that this condition that we wrote over here as one, that we require f prime of z to be continuous in D, this becomes a consequence of this result that is stated over here. But we will not get into that, but it's a remark. So this assumption is not necessary in Cauchy-Goursat theorem. In fact, it arrives or appears, whatever you want to call it, it arrives as a consequence of the result in, let's call this equation 1, 1. So the Cauchy-Goursat is just the generalization of the Cauchy's theorem. Okay, now let's go for a very simple proof. Now we know that we can write our complex variable functions or functions of complex variable, and we can write it as this, right? Or just omitting the x and y's, you can write it as this, like this: f is equals to u plus iv, where the parameterizations are understood. And now what you do is that you write dz is equals to dx plus idy, right? And you just put those things into the contour integral itself. So this is f of z dz, insert some closed contour, and this is u plus iv dx plus idy. There is this integral, and it's a closed contour integral. Notice that we are not using any parameterization, so I'm not using the limits. I'm just using the contour integral itself. Okay, and if you distribute these things, you will have u dx minus v dy. Then the imaginary part of this integral would be u dy plus v dx. At this point, we are going to use Green's theorem from real variable calculus that you see. That is the two-dimensional version of the divergence theorem. Okay, so let me write it over here. Using Green's theorem, we get this will be turned into a double integral, because if you try to see it pictorially, this is how it would look like. This is the, let's say, contour C, and this line integral that is appearing as u dx or v dy, this will become a double integral over this region over here. Okay, that's what the Green's theorem tell you, right? So this u dx would be u dx minus v dy, this would become minus partial derivative of v with respect to x, partial derivative of u with respect to y, and then there would be the integration measure dx dy. Similarly, you will have double integral over this region, or so to say here in terms of this complex analysis, the domain, that is more appropriate to use. This would be just this one, dx dy. Now let's try to focus on the theorem statement. That is, we're saying the function is analytic, right? So if they're analytic, they will satisfy what? The Cauchy-Riemann conditions. So now use the Cauchy-Riemann or CR conditions. That is, ux equals to vy and uy equals to minus vx, right? So ux was what? Is just the partial derivative of u with respect to x. Similarly, uy is partial derivative of u with respect to y, and so on. So if you do that, this keep this vx and this uy you can substitute with minus vx, right? So this is vx minus dv dx, dx dy. This is 0, and this is the imaginary part, right? And the imaginary part, let's try to see what happens with the imaginary part. Ux, that means partial derivative of u with respect to x, was equals to partial derivative of v with respect to y, right? So ux equals to vy. That means using this condition, we can also see that this guy goes to 0, because ux, and if I substitute it, this would be just this, dx dy. This also goes to 0, so this is equals to 0. Hence, we can tell that, or we prove that this is equals to 0 if f of z is analytic inside a domain that is simply connected. Domain that is simply connected and inside the domain we have a simply closed contour on which we are evaluating this integral. Okay, now from here we can also note that Cauchy's theorem can be alternatively stated. That means we can say that if this f of z is analytic everywhere interior to and on a simply closed contour, then this condition over here would hold. What do I mean by that? Let's try to see it pictorially. That's let's say this box is our domain. Let's say this is our domain. We have some contour, simply closed contour, okay, and f of z is analytic everywhere here. Let's mark this everywhere here with the light green lines, and on this points on the contour as well. Then you would have this condition. A closed loop, closed contour integral would result in a 0. Okay. Now, using this result, we can derive some important and interesting results as well. One of them is that if f of z is continuous in a simply connected domain D, and if Cauchy's theorem is satisfied, that means f of z, our closed contour integral, is 0, then for every simply closed contour, for every simply closed contour, let's call them with C, lying in D there exists a function let's call that capital F of Z, which is analytic in D such that f prime of z, that means derivative of capital F with respect to z, is equals to small f of z. What do we mean by this theorem? Well, we know that Cauchy's theorem is satisfied, and from this result, or the theorem itself, you can call it a theorem, you can call it a consequence of Cauchy's theorem, whatever you want, we see that this statement over here actually indicates that if Cauchy's theorem is satisfied, then this condition, that means the conditions in the Cauchy's theorem, and continuous function, that means this f of z, a continuous f of z, will yield an analytic antiderivative for f. That means that if you have some f of z which is continuous in a simply connected domain, that means it's continuous first, and then it's satisfying Cauchy's theorem, right? So that means when it satisfies Cauchy's theorem, you can also say that okay, this f of z is analytic itself. Now after that, you are seeing that, or we are taking it for granted over here, that this f of z is equals to some derivative of another function, capital F prime, equals to z. That means the antiderivative itself is analytic. That's what it's what is trying to indicate this statement over here. Okay, so if you have a f that is continuous and it satisfies Cauchy's theorem, that means itself, the small f itself is analytic, and you want to find an antiderivative of it, that will also be analytic. We will not go to the proof over here. We are taking this for granted without any proof. The proof is also pretty simple, but we are not going to see that over here because we want to discuss Cauchy's theorem again, but this time in a multiply connected domain. And if you recall, that multiply connected domain means you have some holes inside it. That's the most easiest way to recall what is a multiply connected domain. So let's consider, so we are trying to consider Cauchy's theorem in multiply connected domain. Even though Cauchy's theorem stated that it's for a simply connected domain, we just want to see what happens in a multiply connected domain, and we'll see that this will still hold. In fact, this investigation on a multiply connected domain will give us the first idea that counters can be deformed. Okay, so let's consider a multiply connected domain like this. Let's say it has some holes inside it like this. These are some holes. Let's say hole 1, 2, 3. Okay, and the domain, let's say, let me draw the domain like this, even though it's not necessary. Let's say this is our domain, this is the contour, and this contour encloses 1, 2, 3, these 3 holes that is inside the domain. How do we now do this thing, right? Okay, so let's try to make some progress. The idea is that if you ignore this domain boundary, by ignoring I mean I'm not drawing it over here, what you can do is that you can divide this whole contour, that is, let's say, given by C0, because you want to integrate over this contour, into 2 parts. That means first you start from here, you go like this, then you go like this, just avoiding these holes. This is one way, and then you start from here, you go like this, again avoid these holes like this. You can do it like this, or what you can do is that, let's say these are our holes, 3 holes. I want to draw them first. Then you start from, let's say here, go like this, then make a small circle, a semicircle like this. The drawing is not very accurate, sorry about that. So okay, this is another way, so I'll stick with this way. So let's say this is your C0. That means from, let's say, capital A to B, this is the part C0, and then you have this little small lines which are also known as cross cuts, and they're all equal to each other. Let's call this one as L1, then this would be minus L1 because you are going in like this downward direction, but once you make this small rotation around this hole that is represented with a cross, you are going on the upward direction. So if this is called L1, this would be minus L1, and so on and so forth. Similarly, if you can call it L2, this is minus L2, L3 minus L3. So now what we are going to do, at first, if you consider this integration of this f of z along this contour, that means you start from A, go up to point B, and make this small rotations around the holes and come back to A. That means you are going along this direction first, then you have to take into consideration the cross cuts, then you have to take into consideration the small holes. Let's call this hole number 1, 2, and 3. So let's consider this small semicircular thing as C3, this semicircular arc as C2, this semicircular arc as C1. Okay, and what you do right now is that you want to figure out that how to incorporate this thing to the things that we have discussed so far. So this is your full contour integral. Okay, now as I discussed before, what you can do is that since these contours are splitted up, you want to calculate contributions coming from each contours. That means you count the contributions coming from C0, then L1, then C3, then minus L1, and so on. Okay, so a shorthand notation would be to just write it like this. This would be C0, right? Then there would be, also notice that one thing important over here, that this C0, we are taking it as a positive direction because it's like we're going on an anti-clockwise direction, right? However, look at this C3, C2, and C1. This is going in the opposite direction of C0. So if you consider this C0's orientation, or the direction from A to B, as positive, this C1, C2, and C3, they have to be negative. So keep that in mind. So plus, there would be a minus sign at first. The plus is just to indicate that we are adding the contributions. Okay, but the contributions itself can come in terms of a minus form. So there will be a minus, and there is the C3, C2, and C1, right? So let's use the summation notations from I equals to 1 to 3, which would be given as Ci, and then there are the cross cuts. But since these cross cuts are equal to each other, even though the drawing is not very up to the scale, you can always make these crosscuts equal to each other, and since let's say since this direction, let's say this L2 over here, if this direction is positive, this part would be negative, right? Because they are on the opposite direction. So all the crosscuts would cancel each other out. So I'm just writing it as crosscut contributions, and they are simply 0. And then I would write the f of z dz like this. Okay. Now what we have to do right now is that we are saying that if we ignore these f's, all these f's and dz's and so on, we see that the total control integral is nothing but the contour that is denoted by c naught plus, sorry, it should be a minus because there is a minus over here. So minus this I equals to 1 to 3. Obviously we can take more holes. Let's say if you take n holes instead of 3, there will be a n. Okay, and yeah, so this is the thing that we can see over here. Okay, now this is our interpretation of the integral, that if you want a result out of this integral, this is what we would get. But what was our initial goal? Our initial goal was to not leave these gaps over here that you see. Our initial goal, I'm drawing with a red line over here, goal was to use a contour that is a simply closed contour but in a multiply connected domain, right? So what we need to do right now, we need to take some limits where these gaps vanishes. These gaps over here, they vanish. Okay, so if we do that now, then we can see that one contour with the enclosed region boundary by C, that is lying left to C naught and right to our C eyes, form this Cauchy's theorem. What we mean is that if you ignore this diagram for a second and focus on this diagram, you can see that this is one part of our initial goal, that is the C naught. Let's say this is some C prime. We want to actually calculate C prime plus C naught like this. These are our crosscuts and they cancel each other out, right? And finally we will have this circles that is inside our contour of interest, but notice that we have broken up the contour in such a way that in the first phase it goes like this and it avoids the holes, right? So this part individually and this part individually goes to 0 because of the Cauchy's theorem. Similarly, we can see that case over here as well. If you take a look at this part, this black lines doesn't enclose any holes, it goes around the holes. Okay, so the net contribution is 0. And then we do this trick that we are minimizing the distances from these gaps. That means we are going to enclose them because that was our goal. Our goal was to calculate a contour integral in a multiply connected domain. But what we did is that we cleverly avoided the holes in a multiply connected domain so that we can use Cauchy's result and see what we can get out of it. That was the whole idea. So for this region, let's mark it with this color. You see inside this region that are marked with this grayish color and denoted by the black lines, there is no holes. However, the region that is bounded with this red line, there are holes. So inside this region we can use Cauchy's theorem, and that actually goes to 0. Okay, and in the limit where we shrink these distances down so that we can get our original result, that is denoted with the red line, first we use the fact that this guy would be actually 0, and this is equals to C0 minus sum over I equals to 1 to 3 Ci. And finally what you can write is that this contribution is simply equals to this contribution. Oops, sorry. So what does that mean? Let's try to draw it pictorially again. So initially we wanted to evaluate this guy, let's say x1, x2, 2 holes, and this was our contour, right? So since we don't know how to do it, but we have Cauchy's theorem at our disposal, which says that you avoid the holes, you do things in a simply connected region, you can use Cauchy's theorem to make the whole integral go to 0, right? So instead of doing this, what we did is that we carefully avoided the holes. Okay, this is not avoiding, like this. We avoided the holes, and later we reduced the distances between the crosscuts and made this one, right? But what does this result tells us over here? What does this mean? This means that if you have a multiply connected domain like this, let's say there is one hole C1, let's say C2, C3, C4, C5, let's say C of n, many holes, and let's say you have a contour that encloses all of these holes, then the result you would get from this contour C0, that means along this black line, C0, a closed contour, this would be just equals to the sum of all the holes. What do I mean by sum of all the holes? Well, not all the holes, is that you evaluate the functions, or you evaluate the integral for the functions along these small circles that encloses the holes. In fact, you will realize later when we study residual calculus that these points are most of the time called singular points of a function, and they have this non-trivial contribution, and most of the time we'll be interested in finding out that contribution. So here, from here you can write it as this. This is what it means. So that is our discussion for the theory part, the simply and multiply connected domains and Cauchy's theorem. Before we finish, there is one last small theorem, that is that will help us into different kind of counter integrals. This is a theorem I didn't discuss so far. Let's say this f of z, our function, is continuous on a contour C. Then what we will have is that, let's say this is continuous, and we also have another condition. Let's say our upper bound for this function, upper bound for f of z in some domain is M, and the contour that we are interested in has some length L, and the contour of interest this length L, then the modulus of this integral Note that I'm not using a closed contour simple. So it can also be applied for open contours as well. For example, a line, a semicircular arc, and so on. This is equals to ML. How do we do it? How do we prove this? I mean, it's pretty simple. Let's call this I, C f of z dz, right? And now you can use the parameterization to transform this thing into a integration with limits. Let's say a to b z of t, z prime of t dt. And from real variable calculus, you already know this inequality that tells you a b g of t dt, this is less than or equal to a b modulus of g of t dt, right? So use this inequality over here, and if you do that, we will get the result that I is equal less than a to b f of z of t modulus of z prime of t and dt. Pretty simple, right? Now notice the fact that here we said that there is some upper bound for f of z and it is denoted by m. So now we use that information to our advantage. That means I can use the upper bound right now for this f of z of t. So I is equal less than, because this guy, this itself is equal less than m of z prime of t dt. So I itself is equal less than this guy. Now what is this? This is nothing but the arc length. Why? Because if you see that z prime of t dt, and if you take a modulus of it, this means that this is x prime of t. All these primes are just derivatives with respect to t, like this. And what is modulus? It's just a distance, right? So this is just square root over x prime of t. Okay, t should be in a bracket, y prime of t, and there are some squares dt, but x prime of t is what? Dx dt, right? Similarly, y prime of t is dy dt. So ultimately this is just dx square plus dy square, which is nothing but the length. And let's call that length as, or the infinitesimal length as ds. So what we have using all this information is that this is equal less than m integration of a b with ds. And what was our contour length or arc length? Contour of length L, right? So from a to b it has a length of L. That means a, if this is a, this is b, this length is just L. So finally we have I is equal less than m L. So what we have is that where m is the upper bound for the function itself and L is the length of the contour, and this is how we prove it. Why did I prove it? Because it will help us in evaluating improper integrals that we will see after we have studied some Taylor and Laurent series for complex variables, and after that we'll get into the heart of the residue calculus. There we will frequently use these conditions and we will see that we can evaluate some virtually impossible integrals by using this theorem as well. So this will be it for today, and I'll see you guys on the next lecture. Thank you.